Great. Thanks, Ian, for the introduction, and thank you everybody for joining. As Ian mentioned, for my presentation, I'll be discussing rock testing tools and techniques that we've been developing at BGC's Advanced Geotechnical Laboratory. The topics I'll be discussing are the lab's custom rock direct shear machine, lead hardness testing, and I'll provide a few snapshots on some of the ongoing and future rock testing R&D initiatives that we have on the go. So one of the first R&D initiatives in rock testing at the BGC lab was the creation of a custom rock direct shear testing apparatus. It was realized early on while expanding the lab's rock testing capabilities that the testing methodology and equipment typically utilized for rock direct shear testing had several inherent limitations. These limitations were the prep time, machines with rotating systems, and machine friction. So these limitations were overcome with a few different design choices, such as the slab method, linear rail guides, and a triaxial load cell, which I will discuss in the next couple slides. So we use an alternative to the conventional sample encapsulation method, which we refer to as the slab method. With this method, specimens are cut parallel to and on either side of the discontinuity, producing two thin slabs approximately 1 inch thick. These are then glued to steel plates using a high-strength, fast-setting epoxy. The slab method allows for faster sample preparation. We're able to get samples ready for testing in about an hour. Additionally, the sample can be tested in any direction, which allows us to test samples along structures if they're present, such as along slicked sides. We're also able to test a wide range of sample sizes because we aren't confined to a certain mold size. Fundamentally, the direct shear test is intended to simulate planar sliding along a joint surface. At the scale of the joint, the freedom to rotate in any direction is severely restricted, and so should the apparatus that's simulating these conditions. So the figure on the left illustrates a typical conventional sample mold setup, which incorporates a pivot point on the top to prevent lateral movement. However, this setup has sample contact occur preferentially near the pivot point, and this issue often results in stress concentrations and sample damage near that pivot point. So to prevent this, the BGC direct shear machine incorporates low friction linear rail guides, which keep the samples from rotating. The issue of system friction is also poorly addressed in current standards. ISRM suggests measuring the frictional forces of the system or running dummy tests to quantify the forces, but it doesn't provide much guidance on how best to do this. So to avoid the issue altogether, the BGC direct shear machine uses a multi-axis load cell between the sample plate and the lower sled. And with this configuration, the loads applied to the sample, both shear and normal, are measured directly, effectively bypassing the effects of any friction in the system. And we've recently acquired both a 10 and a 50 kilonewton load cell, which we can swap out of the machine to increase our testing ranges and to increase accuracy when we're testing at low stresses. And for more details on this machine, I encourage you to look at the ARMA conference paper written by Ian that's cited here on the slide. So for the next topic, I recently presented a paper on lead hardness testing and its use as a tool for rock strength estimation at the Canadian Rock Mechanics Symposium this past August. This paper was a collaborative effort between BGC and Dr. Andrew Corkum of Dalhousie University. And in the next few slides, I'll provide a summary of this study. So the lead hardness test is a non-destructive rebound test originally designed for metals. It uses a portable device where a spring-launched impact body strikes the specimen, and the rebound velocity relative to the impact velocity determines hardness, and harder materials yield a higher lead hardness value. This principle allows for rapid surface hardness assessment in the field or the lab. Current rock strength estimation methods like the ISRM R values and point load testing have limitations such as subjectivity or destructiveness. Even Schmidt-Hammer testing, though less destructive, can still damage weak samples and make UCS testing on those samples unviable. So Lieb harness testing offers a rapid, non-destructive alternative with demonstrated correlation with UCS, enabling a more efficient and higher resolution field measurements. So BGC and Dalhousie University host a Lieb harness and a UCS database of over 790 tests that have been compiled from external studies as well as our internal testing. So our lab provides Lieb harness measurements on all of our direct shear and UCS and triaxial reports, which has resulted in 65% of this data being collected here at the BGC lab. This comprehensive database has allowed us to conduct statistical analysis and correlation modeling for rock strength estimation. So correlation between Lieb harness and UCS is modeled using a nonlinear power regression described by the equation shown here, which was found to provide the best fit in a previous study by Dr. Corkum. The correlation fitting parameters vary by rock type and highlight the importance of rock-specific calibration for accurate strength predictions. It's clear from the goodness of fit parameters that there is a wide distribution of data. So a sensitivity analysis was conducted on the alpha values for each rock type to create 50% confidence intervals. And this method provides a range of correlation values that can be used to estimate a high, average, and low UCS based on Lieb readings. An outcome of this study was the following table. This table summarizes the Lieb ranges for each ISRM field strength R grade based on the best fit correlations and box plots. As part of BGC's core logging procedure, field Lieb testers are now being brought to site investigation drill programs, along with this table to help field staff estimate rock strength in the field. Additionally, BGC collaborated with the Geotechnical Center of Excellence at the University of Arizona and Rio Tinto on a Lieb harness case study. The study utilized drill core from the Bingham Canyon mine and focused on establishing a correlation between Lieb hardness values and traditional hardness R values in PLT data. After analyzing the quartzite and monzonite data, the study showed Lieb hardness had a moderate correlation with R values in PLT. Now I'm going to switch into providing a few snapshots into what we're currently working on and what we're hoping to pursue regarding rock testing research. So the BGC lab has a GCTS rapid rock triaxial testing machine. It's a closed loop, digitally servo controlled system with confining pressure and pore pressure control systems. This machine allows us to work with clients to develop custom procedures that require an advanced rock testing apparatus. One example of this is the work we've been doing recently with Shane O'Neill from O'Neill Hydrogeotechnical Engineering to complete custom hydrostatic compressibility testing. These tests are comprised of several stages of hydrostatic loading and unloading following the stress path shown here, while maintaining a constant pore water pressure in order to quantify bulk rock and pore compressibility. The system is also capable of conducting multi-stage triaxial tests, but some of our early testings indicated the need for a better next stage indicator, which is an area of research we're planning to pursue. Recently, we started conducting ultrasonic pulse velocity testing on all of our UCS and triaxial samples that come through the lab. We completed a testing program for AngloGold Ashanti a couple summers ago, and they requested that we take UPV measurements on all of their samples before testing, and they actually lent us their device to do so. The results shown here are from the study, which they recently published at the Slope Stability and Mining Conference, which shows a UPV tester can accurately identify strength class. So based on these results, we purchased one of these devices, and we've been using it to build a database of UPV measurements to assess its efficacy for strength and modulus estimation, similar to the Lieb study that we did. So as part of the direct shear testing procedure, we take a 3D point cloud scan of each discontinuity surface before and after direct shear testing. We've been doing this for a couple years now. We've been building a database of scans and direct shear testing results. We're now working with Dr. Andrew Corkum and his master's student, Stuart Cowper, on a study utilizing this data to investigate numerous roughness quantification methods to identify a practical approach that can be deployed in both the field and lab settings. The goal of this study is to substitute JRC and subjective parameters with something that's more repeatable and measurable. This is an example of a preliminary workflow that Stuart has been using to quantify roughness. For this method, linear profiles are extracted from the point cloud and then fit to a horizontal line of best fit. And then this can then be used to calculate roughness parameters such as the Grasselli roughness parameter. Scans can also be used to calculate 2D and 3D roughness RA values, which could be linked to measurements in televiewer scans via BGC's Structura program, which Eric Wilton is giving a presentation on in the next session, and I highly recommend watching that. Beyond calculating roughness from these scans, we're also looking at using the data for shear strength prediction. We're currently assessing existing strength criteria using our database of sample properties and test results to find a predictive strength model that utilizes easily measured inputs. Finally, we've managed to merge all of our rock testing report results into one database separated by test type. This includes over 500 UCS, 600 TCS, and 500 direct shear results. We're also in the process of compiling and tagging all the metadata that's associated with each of these samples that may not have been provided to the lab when we were testing, things like rock type, strength grade, weathering grade. This database has already been useful for some of the topics I've already mentioned. And having all this data in one place so far been very powerful for finding distributions and correlations across a wide set of data. We're also hoping to leverage it for data-driven strength and behavior prediction, possibly through machine learning techniques. So overall, all the initiatives I've discussed today have been in the pursuit of these three goals: to enhance rock testing procedures, either through upgraded equipment or optimized procedural standards, to elevate field and material characterization practices by way of laboratory trials, or to leverage our high volume data acquisition to enable advanced analytics and data-informed decision-making. If these goals align with your own and you have an experiment you'd like to pursue, we're always looking for client partners to engage with. So please feel free to contact me, whether it be about research initiatives or rock testing programs that you may have.